Usually, okay. Usually, no. Matrix by okay. I guess everything is being recorded, and yes, I am audible. Okay. So most of the time we say, okay, this is a matrix is a rectangular array of numbers or whatever, like this: a1, an, an plus 1, like this, whatever. But this is not a very mathematical description of a matrix. So what do we mean by a matrix? Is basically a m cross n matrix over a ring R is a mapping from to R. Okay, so this is all for, I mean, it is not very formal conversation. I mean, just some, I am trying to give you some definitions, and then I will start formally. So what is that? A matrix is basically, you say that the mapping from the set 1 to m to 1 cross 1 to n to R. This is m cross n matrix. Okay. So what basically is that you have R power, suppose you have an element R power mn. We all know what we mean by R power mn: Cartesian product of R mn times. As a set, Cartesian product of R mn times. But since R is a ring, you can give R power mn a ring structure also by component wise addition and multiplication. You can check that by component wise addition and multiplication, R power mn becomes a ring. If you have two different rings, say R and S, you can take the Cartesian product of these two sets R and S, and you can define component wise addition and multiplication there also, so that R cross S becomes a ring. Okay, so now you are taking cross product of R mn times, but Cartesian product, and take an element A from mn. That's a that's is kind of a long list of number. So basically, what is basically it, we are just, okay, chopping it off from some, okay, this is some m, this is 2m, this is 3m, and this is mn. So basically we are chopping it off and place it in like that. So it is easier for us to handle with this thing. It is a lengthy thing to blah blah blah, all these things, whatever. So why these two things are same? Because if you look at the definition of Cartesian product, the Cartesian product of two sets is just basically, okay, if I go back to the definition of Cartesian product of two sets, say and A and B, then it is a function is a function f from 1 comma 2 a union b such that f1 is in a, f2 is in b. If you have a function from 1 comma 2 to union b and collect all the functions of this form, the set you will get, and the set a cross b is defined in our class 12, that a belongs to a and b belongs to b. These two sets are biject. These two sets, you can establish a bijection between these two sets. Collection of all functions like that and the sets of these forms, you can give a bijection between them. So formally we can write them like that, but actual definition is this. So what we are doing, it is m number of element cross n number of element. So basically it is a cardinality of mn sets. So you are giving a map from this to this. So so what is it? It is the Cartesian product of r power mn, and this is the same thing. These two are same thing basically. So this is all this some kind of heuristic thing, but we usually, when we say this is a matrix, we refer to this form, not on this form. Okay, there are some rectangular number of array, m number of row, n number of columns, blah blah blah. We are saying, okay, this is number of food, number of clothes, number of this, number of that, and how many numbers of that, all these things. But okay, but informally speaking, that whenever we are saying that, oh, a is a matrix, we are saying that, okay, a is looks like this, and entries are coming from some ring or some field, whatever. Okay, all these things. Okay, now suppose we have a system of linear equation. Suppose we have a system of linear equations, a11 x1 plus 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 a it is 1 n xn equal to y1 or b1 a m1 x1 plus 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 a m n xn equal to bn. Suppose you have a system of linear equation like this. Let's say something star. So note that you can write them as ax equal to p, where a equal to this matrix a11 a 1n a m1 a mn. X is the variables x1 dot dot xn, and b is b1 dot dot bn. And whenever we are saying ax, this means a11 x1 plus dot 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 a1 in xn and a m1 x1 a mn xn. The usual multiplication that you have learned from class 12, it is a m cross n matrix. This is a, okay, it is a m cross n matrix, right? This is something n cross 1. This is a n cross m or m cross n matrix. And this is a 1 cross n matrix. So if you multiply them by ordinary matrix multiplication, and you are getting some 1 cross n matrix here also, and it is also 1 cross n matrix. So you are, and these two matrices are same, if and only if their all components are same. So from here you will get the previous equation, that star. So it is sometimes it is better to write a linear equation in form of matrix, It saves lots of space and helps us to compute the things. That's the thing, that you can write a system of linear equation in matrix. So our original goal was to find the solution of linear equation, and the one process is the Gauss elimination method. And okay, so what we are doing, okay, multiply any equation from there, and you are basically eliminating the number of variables, and then you get a system of linear equation where you can find the solution easily, and then you are coming back to the previous equation, and these two solution matches because they are the equivalent system of solution. Okay, so now we have basically greater technique to let's say the greater technique to eliminate all these variables. Okay, definition. Let A be a matrix M cross N matrix. Okay, so we define elementary row operation on A as follows. Okay, how to write? Okay, this is very informal. Swap any two rows. B scalar multiplication non-zero element. Multiplication by some non-zero scalars to any rows, any row. Multiplication by some non-zero scalars by some non-zero, and add with any other row. So elementary, to define elementary row. Okay, so what are the elementary row operation on a matrix? Basically, you take a matrix, say A11, A12, A13, A21, A22, A23, A31, A33, A32, A33. Suppose you take a 3 by 3 matrix, and you can swap any two rows. So what suppose you want to swap the first and second row. Okay, A22, A23, A31, A32, A33, A21, A22, A23. This is the elementary row operation if you apply the process A. If you suppose you apply the process B, you want to multiply by any number, any non-zero number, say 5. Okay, A11, 5, A22, 5, A33, 1, 2, 1, 3, A21, A22, A23, A31, A32, A33. If you apply B, if you apply C, multiply any non-zero number. Say I want to multiply it by 5 and then add it to the first one. So a11 plus, let's say multiply it by 4, a21. This is the first entry. a12 plus 4, a22, and a13 plus 4, a23, and rest of them as usual, a22, a23, a31, a32, a33. So these are the elementary row operations that you can do on matrices, that you can swap any two rows. These are, I am not writing them in mathematical manner, but you can write, and you can swap any two rows. You can multiply any non-zero number to any rows, and multiply any non-zero number and add to the add to any rows. So what is the motivation for this kind of definition? Motivation is, you can take the motivation from here, where it is, okay, here. If you suppose you have these two system of linear equation, let's write them in matrix form. xy equal to 3, 4. Okay, so what you can do, if you take the matrix 2, 1, 1, 1, you can multiply the 2, 1 and multiply the bottom row by 2. Yes, you can. If you apply b, if you apply, okay, if you now apply c, 2 minus 2 plus minus 1 into 2, 1 plus minus 1 into 2, 2. This is the same as, this becomes 0, this becomes minus 1, this becomes 2, this becomes 2. If you again apply a, yes, a, now b, multiply by 2 inverse, 0 on the bottom row, 1, 1. So you see that you get this equation, that x equal to minus, okay, it is y, whatever, yes, y equal to minus 1 and x plus y equal to 4. You get this equation. So what are you doing here? That you want to eliminate some variable. Okay, so what I have done, that 2x plus y equal to 3, I'm and subtracted this equation from this. Basically 2x minus x is x, and y cancel out, equal to minus 1. So basically you get this, and you are doing the same thing on matrix, but okay, you get minus y, that's no problem. You are multiplying it by 2. If you multiply directly, you have different yes, if you okay, if you want to apply c here, you will get that 1, 0, 1, 1. So if you apply c here, you get that. If you apply this type of operation, you will get this man. So anyway, you have reduced your equation so that you can solve them now. So what is that? If you get x equal to minus 1 and y equal to 5, and here you get x equal to what? X equal to 4 or x equal to minus 1 again, yeah, and y equal to 5. So the basic goal is to reduce the equation and reduce the number of variables so that you can easily solve them. Whatever you are doing in this format, you have transferred all the things into matrices so that you can write in a more compact settings and solve the equation. That's the motto of the whole thing. All these things are very heuristic, but but what I can say that these are very okay. Okay, elementary row operation theorem. To each elementary row operation, there exists another elementary row operation of same type such that row operation say e plus such that e plus of a equal to a and e prime of p of a equal to a. Proof. Okay, suppose you have a matrix, you have applied the type, if you applied the number a procedure that you swap any two rows. So if you swap any two rows, you can swap them back so that you get the original matrix. If you uh, use the process B, that you have multiplied any row by any non-zero scalar, since you are on the field, you can multiply by it inverse, say C inverse, so you get the previous equation, the original matrix. And if you apply number C, that you have multiplied any row by any non-zero number, then add it to another row. So what you can do is that you multiply the same row by C by, okay, let's say C, uh, okay, you multiply by minus C and add it to the same row, but you get the previous equation and they are all the same types. So okay, now write it formally. Suppose this one, if E goes rapid, that is, if A is a M cross N matrix and E swaps the ith row with jth row 1 less or equal to I, j less or equal to M, then we can we can swap the jth row with ith row again. All these operation E prime such that we get back the case 2. If E is multiplication by any non-zero scalars, then since scalars, say C, since C belongs to F and C not equal to 0, C inverse belong, oh, not F, is K. F inverse belongs to K. Now scalars C to the ith row. C to the ith row. Now multiplication, now multiply the ith row by C inverse so that we get back A. Case 3. If is multiplication by any non-zero scalar C to row I and then add to row J, then we can multiply row I, we can multiply minus C to row I and add to row J to get back A. This completes the proof. Definition. Let A comma B belongs to M n cross M. We say A and B are row equivalent if B can be obtained from A by a finite number of row operation of elementary row operation, finite number of elementary row operation. Finite number of elementary row operation. You may check that this is an equivalence relation on M n cross n over K. That is A is related to B if and only if A are, if and only if A is row equivalent to B. A is row equivalent to B. Okay. Definition. Let I n belongs to M n R be the identity matrix. we say A belongs to MNR is an elementary matrix elementary matrix if A is obtained from IN by a single elementary row operation. Of any type. That is, suppose you have suppose IN is 1 1 1 0 0, the 3 cross 3 matrix I3. So what you can do, that A can be, if you apply the elementary row operation once, suppose you want to swap the first and third row, it becomes 0 0 1 1 0 1 0 and 1 0 0. This is an elementary row matrix. C 0 0 0 1 0 0 0 1. This is an elementary row matrix. A equal to, example, A equal to, let's say, C 0 0 C 1 0 0 0 1. Zero, 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 1. I have added this row. I have added this row with this row. So this is an elementary row matrix. This is not an elementary row matrix. This is not an elementary row matrix. Multiply by some number here and add it here. Oh no, it's fine. Multiply this and then add this. No, it's fine. It is an elementary row matrix. I have multiplied it by some number and then added to this row, second row. So all these are, these are the few examples of elementary row matrices. These are the few examples of elementary row matrices. Okay, so now we can produce as many as many elementary matrices as you can.
That হার্ডেরটা কি করে হলো একটা স্টেপ?
ওই যে multiply it by C and add it to the this second row by this C type C operation.
তাহলে তো আমরা দুটো স্টেপ ইউজ করছি।
হ্যাঁ হ্যাঁ, না 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 না, এই তো এক মিনিট, just a minute. Multiplication by some non-zero scalars and add with any other row. I have multiplied it by C and then add it to this row.
C operation.
হ্যাঁ, type C operation. This is type C operation. This is type C. This is type B. This is type 1. Type A. Now you can produce as many elementary row matrices as you can. Okay. So these are the few examples of.
First row 100.
হ্যাঁ.
The type C and first row তাহলে 100 হবে না?
Oh yes. It is 100. Yes. Yes, it is 100.
না আমরা সি দিয়ে মাল্টিপ্লাই করছি ফার্স্ট রোটা, দেন সেকেন্ড রোর সাথে অ্যাড করছি।
হ্যাঁ, কিন্তু ফার্স্ট রোতে কোনো এফেক্ট পড়বে না। সি দিয়ে মাল্টিপ্লাই করে অ্যাড করবে, ফার্স্ট রোতে কোনো এফেক্ট পড়বে না। ঠিক। Okay, it is 100. Yes. Okay, 20 theorem. Mm, just a minute. Elementary row matrices. Mm, right. Okay, so do you know that what do you mean by generator of a group? What do you mean by generator of a group? You all have learned group theory, right? And you should know what do you mean by generator of a group.
If there is an A element in G such that one element of G is A power n for some angles to make.
That is
Mm.
okay. G is generated. That is G is generated by one element. G
Okay.
may that is G is cyclic, but G may have more number of generators. I am saying that G may have two generators. You cannot write G as a product of one element. You have to use two elements to write every element of G in the product of them. Then G may have generators of number 2, number 3, or infinite number. We don't know. But basically, what is, suppose S is a subset of G. S is the generating set of G. If every element of G can be written as product of powers. Suppose S is S1 dot Sn. Let's say S is finite, S1 dot Sn. So if you take any G belongs to G, you can write G as S1 power R1, S2 power R2 dot Sn power Rn, where R1, R2 are positive, where R1, R2 are integers. This R1 may have positive, may be positive, may be negative. I don't care. It may happen. But R1 positive, R1 integer, R2 integer, Rn integer. If you can write every element of G in this form, then we say that okay, S is a generating set for G. Now, if S has a single element, then it reduces to the case whatever you have said, that S is generated by a single element, that is S is G is cyclic. But G may have different number of generators. For example, if you look at the Sn symmetric group, it has at least two generators, 1 2 and 1 2n, this n cycle and 1 2. If you look at Dn, it also has two different generators. It also has two generators, a rotation and a multiplication, and they have some rules that Rs R inverse equal to R inverse and R power n equal to 1, S square equal to 1. These are the rules, and these all the rules generate the whole group Dn, the dihedral group of order n. So, and okay, Z mod nz has single generator 1, or any number that is co-prime with n, they are all generators of Z mod nz. So Z mod nz is cyclic, but Sn or Dn, they are not cyclic. That is, they may have different number of generators. Okay. Now, so now MNK is a group. You know, MNK is a MNK, not MN. I mean, yes. I mean, if you not group, but it is a semi group that you can multiply any two numbers of MNK basically. So can you say that the set of all elementary row operation of MNK is a generating set? Can you say that set of all elementary row matrices are generating set for MNK? Okay, can you say that? Suppose A B belongs to M cross N are two matrices such that A is row equivalent to B. Then the system of homogeneous equation Ax equal to 0 and Bx equal to 0 have same solution. So basically this theorem shows that why we are interested in row operations, because if you can give some row operation on a matrix so that it becomes some nice in that sense that it has few number of rows, if it has few number of non-zero rows, it has some uh, few number of non-zero rows, and each rows has fewer number of non-zero element, then the then computing the solution of this equation becomes easier. Therefore we are interested in the row in the elementary row operation so that we can reduce our task to some simpler matrices to get our solution and then get back to the original solution because they are equivalent. So basically what we are trying to show that if we have two different row equivalent matrices in the homogeneous system of equation have same solution. Okay, since A and B are row equivalent, we can get B from A if R by a finite number of row operation. Finite number of row operation. Okay, finite number of row operation. We will show that okay, finite row operation. Suppose B is obtained from A via C1 dot CR matrices. That is C1, C2. That is, you have applied some row operations to get C1. If you have applied another row operation, get C2, and after doing some finite number of steps, you get CR, and then applied again, so you get B. We will show that Ax equal to 0 and Ci we will show that Cix equal to 0 and Ci plus 1 x equal to 0 have same solution. that is they are equivalent system of linear equation. Equivalent system of linear equation. Okay. Now note that C1 is obtained from A by a row operation. That is, every equation in C1x equal to 0 is linear combination of every equation of Ax equal to 0. On the other hand, A can be obtained by C1 via inverse elementary row operation. That is, every equation of Ax equal to 0 is linear combination of every equation of C1x equal to 0. This shows that Ax equal to 0 and C1x equal to 0 are equivalent system. Of linear equations. Hence, they have same solution. Now apply the same process to every step to show that x equal to 0 and bx equal to 0 are equivalent system. And hence they have same solution. Okay, is it clear? Is it clear? Tamanna, you may leave. You have classes. So you may leave. I will stop here. Is it clear to everyone? Basically, I have to row reduced. I have A or B are row equivalent. I want to say that Ax equal to 0 and Bx equal to 0 has same solution. How can I show that? Suppose you have applied a row elementary row operation to A to get C1, then C2, then C3, and so on, and then after some finite step you get B. So basically we want to show that ax equal to 0 and c1x are equivalent systems, c1x and c2x are equivalent system, crx and bx are equivalent system. So they are, so all the solutions are same, and so ax and bx have the same solution. How can we do that? Now notice that you have applied some row operations to a1 to get c1, a to get c1. So every row of c1 are either row of a, or they are some linear combinations of the row of a, and vice versa, that you can apply the inverse operation on c1 to get a. So every row of a is either a row of c1 or some linear combinations of row of c1. So these two systems of linear equation, they are equivalent and hence they have same solution. And this applied for all the c1, c2, cr and b, and therefore ax equal to 0 and bx equal to 0 have same solution. This is basically the idea. Okay, so since Tamanna left the class, I cannot say anything further. If you have any solution, have any doubts, you can ask, or if you want to ask some question or discuss something, you can say right now. We have a lot of time. Or if you want to leave, you may leave. What do you want? You want to leave or you want to discuss something else?
আচ্ছা, তোমাকে আমি যেটা জিজ্ঞেস করেছিলাম যে ইকুইভ্যালেন্ট সিস্টেম লিনিয়ার ইকুয়েশনের ওখানে যে কে আর এন এর ব্যাপারটা,
এক মিনিট,
তার মানে